Improper integrals. The integrals we have studied so far represent signed areas of bounded regions. In this video, we will look at a couple of different kinds of integrals. We will study a procedure for evaluating integrals that has either or both limits infinite, or an integrand that approaches infinite at one or more points in the range of integration. In either case, the integral is called an improper integral. Therefore, there are two types of improper integrals. An improper integral of type 1 is an integral whose limits of integration include plus infinite or minus infinite, or both. An improper integral is of type 2 if the integrand has an infinite discontinuity in the region of integration. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. Definition of an improper integral of type 1. There are essentially three cases of improper integrals of type 1. The first case is defined as follows. We say that the improper integral converges if the limit exists and is finite, and that it diverges if the limit does not exist. Improper integrals are just like definite integrals, except that the lower and or upper limit of integration is infinite. Now I will show you step by step how to evaluate an improper integral. Basically, evaluating an improper integral is a three-step process. First, express the improper integral as the limit of an integral. That is, rewrite it using a limit and a definite integral. We will replace the infinity with the variable b. Second, evaluate the definite integral by whatever method works. We find the antiderivative and then we use the fundamental theorem of calculus to evaluate the antiderivative over the interval from 0 to b. Third, evaluate the limit. Now we get rid of the integral and we have a limit to find. We take the limit of the result as b goes to infinity. When b approaches infinity, the limit approaches. Since we get a real number answer, we know that our integral converges. So the improper integral is equal to 1. The second case of improper integrals of type 1 is defined as follows. We now evaluate item b. We follow the three-step process. First, we express the improper integral as the limit of an integral. Second, we find the antiderivative, and then we use the fundamental theorem of calculus to evaluate the antiderivative over the interval from a to 1. Third, take the limit of the result as a goes to minus infinity. When a approaches minus infinite, the limit approaches minus infinite. Since the limit does not exist as a finite number, the improper integral cannot be evaluated, and therefore, the improper integral is divergent. The third case of improper integrals of type 1 is defined as follows. We now evaluate item C. In this case, we have got infinities in both limits. We start by splitting the integral into two separate integrals. We can split the integral up at any point. So let's choose c equals 0, since this will be a convenient point for the evaluation process. The integral becomes we now compute each integral separately, following the three-step process. Since both of these integrals are convergent, the integral we were actually asked to deal with is also convergent, and its value is given by p over 2 plus p over 2. The second basic type of improper integral is one that has an infinite discontinuity at or between the limits of integration. In other words, an integral over a finite interval from a to b is improper if the integrand becomes infinite at one or both of the endpoints of the interval. Definition of an improper integral of type 2. Improper integrals of this type are defined as one-sided limits, and they are called improper integrals of type 2. Just as there are three types of improper integrals of type 1, there are also three types of improper integrals of type 2. The first case is defined as follows. We solve improper integrals of type 2 in the same way as we did improper integrals of type 1. At first sight, this integral does not look like a particularly daunting integral, and you may be tempted to evaluate this as a proper integral. But the integrand has an infinite discontinuity at x equals 4. The presence of this discontinuity at the upper limit of integration forces you to evaluate this one as an improper integral. The problem point is the upper limit, so we are in the first case above. From this point, improper integrals of type 2 are solved in the same way as we did improper integrals of type 1. We follow the three-step process. Pay attention. The second case is defined as follows. Let's see how it works. We can see that the integrand has an infinite discontinuity at x equals minus 1. The presence of this discontinuity at the lower limit of integration forces you to evaluate this one as an improper integral. The problem point is the lower limit, so we are in the second case above. From this point, we follow the three-step process. Pay attention. The third case is defined as follows. We can see that the integrand has an infinite discontinuity at x equals 0, and the discontinuity occurs in the middle of the interval. So we are in the third case above. We start by splitting the problem into two integrals. From this point, we follow the three-step process for each integral. When c approaches 0 from the left, the limit approaches minus infinite. Since the limit does not exist as a finite number, the improper integral cannot be evaluated. If either of the two integrals diverges, then the original integral diverges. One of the integrals is divergent, which means the integral that we were asked to look at is divergent. We do not even need to bother with the second integral.